All right. So we're gonna, let me get a little bit more situated here. Okay, so right before the holiday and looking at the fireworks and everything, we were talking about charges, and we had actually written down that I have force, if I'm doing gravitational, it's going to be big G, mass 1, mass 2 over r squared. And then we have force for my electric force is going to be K Q1 Q2 over r squared. All right. So in your book, you have a table. Here's our table. It's got a handy dandy information. You can look up a variety of things. One thing we're going to write out is G, which is my gravitational constant. I got to change my glasses. G is my gravitational constant, and this is 6.67 times 10 to the minus 11. And this is in Newton meters squared, kilograms squared. The mass of an electron is going to equal 9.11 times 10 to the minus 31. The mass of a proton is 1.67 times 10 to the minus 27, and these are in kilograms. And my charge on an electron is a negative 1.60 times 10 to the minus 19 coulombs. And then what we want to do is we want to do a Bohr radius. Now, a Bohr radius is the radius of the hydrogen atom, and that's 5.29 times 10 to the minus 11 meters. Oh, and I need my one more thing. I need K, coulombs constant. And K can be 8.99 times 10 to the 9th. Or a lot of times people will just use 9 times 10 to the 9th. And that's Newton meters squared, coulombs squared. And that is also equal to, since we're in the summertime, I want to go ahead and show you that that's equal to 4 pi, this epsilon, and this epsilon is known as the permittivity of free space. And that is 8.85 times 10 to the minus 12 coulombs, Newton meters. That's a square, and that's a square. So we'll see this later on as we work problems, and we'll see a variety of different things as we work problems. But the whole reason we want to do this is we want to compare the gravitational force to the electrostatic force in a hydrogen atom. All right, so that's what we're actually going to do. We're going to compare those two things in a hydrogen atom. Now, if I do my gravitational force, I'm going to get 6.67 times 10 to the minus 11, and I'm in Newton meters squared, kilograms squared. I'm going to do this, and my hydrogen atom is a proton with an electron going around. This is my Bohr radius. And that's what we're comparing. Now, the direction of my force, remember we got direction of the forces, these are attracted to each other, and they're going to be pulling into each other. So this one, I'm going to have to use the mass of the electron, 9.11 times 10 to the minus 31 kilograms. And then this one is the mass of the proton, 1.67 times 10 to the minus 27 kilograms. All divided by my Bohr radius squared. And I've got 5.29 times 10 to the minus 11. And that's in meters squared, because I'm squaring it. Now, one of the reasons I also like to do this is to caution people about their calculators. Depending on how your calculator is set up, you're going to have some interesting things, because we are dealing with some pretty significant exponents here. We're dealing with some significant exponents. So I'm going to go do my 5.299 or 29. So I'm going to clear that one, 5.29. I'm going to use my exponent key on my calculator, and I'm going to put in the minus 11. I'm going to hit enter so I know it's in there. Because sometimes if you don't hit the enter, and depending on what your calculator does, you may be only squaring the 10 to the minus 11. So you have to be very careful about how your calculator is doing things. So this number squared ends up being 2.798 times 10 to the minus 21. And that's in meters squared. Now I want to show you something. If I do my 5.29 and I square that, I'm going to get 27.98. But if I double this, look at how we play with our exponents. This is actually times 10 to the minus 22. So there's a reason that I can take those scientific notation numbers outside. Now, if you haven't played with exponents in a while, you may want to do this, because this will help you out when you're working your homework problems. Am I in the right place? Okay. So these two numbers are the same, because this is written as 27 and that's 2.17. And I've got minus 22 here. This is all great. Because what happens is I can simplify this in my calculator to be 6.67 times 9.11 times 1.67, all divided by 27.98. And I have times 10 to the minus 11 times 10 to the minus 31 times 10 to the minus 27, all divided by times 10 to the minus 22. Now, if I'm doing this, I can add. So it's minus 11 plus minus 31 plus minus 27 divided by minus 22. If I do that, 11 plus 31 plus 27. I get 69 on top, so I get a negative 69, and I have a negative 22. But if I'm adding those, I'm gonna do a negative on this one, because I'm gonna subtract, so it's minus 67 minus a minus 22. So this ends up being a negative 47. So this answer would be times a negative 47. And this is one way you can check to make sure your calculator is working properly. So if I do my 6.67 times my 9.11 times my 1.67 divided by 27.98 gives me 3.63 times 10 to the minus 47 newtons. Times 10 to the 47 newtons. And if you look at example, this is one of your examples in your textbook. But I wanted you to show you this because you want to be able to verify, is your calculator giving you your right exponents? And we used to have to do this before we had calculators. Right? This is how you could take care of and deal with a variety of big numbers. So that's the force due to gravity between a proton and an electron. But now let's do it for our electrostatics. So now I'm going to do the force is going to equal, and I've got my 8.99 times 10 to the 9th. And this is Newton meters squared, coulombs squared. I have a negative 1.602 times 10 to the minus 19 coulombs. I have a positive 1.602 times 10 to the minus 19 coulombs, all divided by my Bohr radius, which we said was Bohr radius squared, which we said was 2.798 times 10 to the minus 21 meters squared. And when I do that calculation and I put it in my calculator, I'm going to end up with a negative 8.2 times 10 to the minus 8 newtons. But if I'm looking at just the magnitude, I have times 10 to the minus 8 compared to 10 to the minus 47. We don't have to worry about my gravity. Don't have to worry about that gravity at all, because that is so far down in the weeds. I don't have to deal with that. I don't have to deal with that, and it's way down in the weeds. But there's two parts that I want you to get. One is that my electrostatic forces are strong. It's going to be relative to my R squared. And I also wanted to show you how to verify that your calculator was giving you the proper number. So I really wanted to make sure that you guys saw that. So questions?